sorry, it turned out it wasn't Elvis. I can't, there's no defense. My eyes, they're sad. Anyway, so I wanted to talk more about definite integrals. So we saw last time their interpretation as areas caught between a function's graph and the x-axis. So I wanted to talk about a few properties that it turns out these definite integrals end up observing. You'll notice there's a list of 5 here. I'm only planning on talking about the first 3 for now. 4 and 5 are probably going to put a separate video. I'm doing them sort of in what I consider, order of how intuitive they are. So the first 3, I think, are pretty intuitive to understand. 4 and 5, we may need to dig in just a little bit deeper. So anyway, so first order of business. So say we have a definite integral of some function, and we have a constant sitting in front of it, k. This probably is not going to be all that surprising to you. The constant kind of comes along for the ride. We can take it out front of this thing. Again, that's pretty, par for the course at this stage. We've been pulling constants out in front of stuff all semester, from limits, from inside derivatives, anti-derivatives. Yeah, hopefully that feels pretty straightforward at this stage. Property 2 is technically 2 properties put together. So some textbooks will list them separately, but so you'll have like a sum rule and a difference rule. The Best's friend sheet, I think, has them listed separately as well. But in terms of being economical with board space, addition and subtraction are going to behave an awful lot alike, and it's the same thing we've seen with limits and with derivatives. You get the idea. So so we can split a definite integral up across an addition or subtraction just like we could an indefinite integral or any of the other calculus operations we've seen so far in the course. These are sometimes referred to as linearity properties. Don't stress about what linearity means in this context, but yeah, that's something. But yeah, hopefully these feel kind of natural at this stage because we've been breaking things up across addition and subtraction for a while now. Property 3, so looks like Professor Carroll kind of slipped writing right here. The definite integral of f of x is we let x go from a to a again. That's not a typo in this part. Every now and again we do need to worry about that sort of thing. And as it turns out, 4 and 5 can leave for now. Like I said, they're not going to show up in this video. We'll get to them momentarily. But it might help to envision this in terms of a picture. So imagine my wonderful, beautiful, generic, mathematician's function, again, right here. So from A to A, we've got that guy right there. And if we ask ourselves, what's the area that we've captured? Well, what is that really? It's a line segment, right? It's a one-dimensional object. One-dimensional objects don't have area. That is fundamentally a two-dimensional quantity. So we don't have any area here. As such, the value of that definite integral, if our limits of integration, this is the lower limit, the upper limit, hopefully that stands for reason. But if they're the same, the definite integral has a value of 0. We've captured no area. So I think that seems hopefully pretty intuitive. All right. So no matter how complicated this thing right here is, if these limits of integration are the same, you're going to get a 0 back. I wanted to dig in and play around with these linearity properties 1 and 2, a bit before we call it a video. So let's take a look here. So we have gone through great pain and hardship coming up with values for a few different functions. So f of x, g of x, and h of x. So we've cranked out values for these and interpreting areas or something else that we might need to do if we don't get distracted by thinking we saw Elvis. So the value of the definite integral of f from 0 to 2 is 4. For g of x, we get -1. We get 3 for h of x. It turns out we need to combine these things in some way, shape, or form. So now it's important to point out these particular tricks only work if these limits of integration are all the same. If this integral here was running from 1 to 5, then we can't quite do the same tricks. But so long as they're all going from 0 to 2, we're hunky-dory. So if we wanted to work out the definite integral of this guy, you might get worried we have to go back to the drawing board and go reinterpreting all of this stuff. As it turns out, no, we can use our properties of definite integrals to break this thing up, so we never really need to worry about anything other than f or g at a time. So our sum difference property lets us break this up into two separate definite integrals, and then the constant property, the constant multiple property, if you will, lets us kind of yank the 3 and the 2 out front. So this thing would break down like so. So 3 times the definite integral of f of x as x goes from 0 to 2, plus 2 times the definite integral of g of x as x goes from 0 to 2. And we know the value of this guy. He's 4. We know the value of this guy. It's -1. So we have 3 times 4 plus 2 times -1. That's 12. That's -2. So we get an overall value of the definite integral of 10. Okay? Let's try another. So if we have we'll still use f of x, but I'm going to toss h of x in there instead. Again, we have to have the 0 to 2 thing, because if this had gone over different limits of integration, the same linearity trick doesn't apply. Same deal. One-third is still a constant. He's a fraction, but that's still perfectly fine. He's a numerical constant. You can take him out. No judgment here. And now we can fill in the values we know for the integral of f of x and the definite integral of h of x. 4 times 4 from the first guy, minus 1/3 times 3. This is 16. This would end up giving me a -1 if I'm doing my arithmetic right, and I'm pretty confident I am. So our definite integral for this combination of the functions would in fact give us 15. So those are our linearity properties. Hopefully they seem pretty straightforward. If not, feel free to ask me questions. So I do want to dig in to those properties 4 and 5, but I think they probably deserve their own video. They may come get me.